Hey everyone, and welcome to the first video of Lecture 11, which is our final lecture of the inorganic part of Chemistry 2. And in this lecture, in this series of videos, we're going to be looking at chemistry in society and kind of applying some of the things we've seen in the textbook and learnt so far, actually looking at where they crop up in real world chemistry and applications. So I've done it in three parts. This first one, we're going to be looking at electricity and what makes things insulators, conductors or semiconductors and how they're applied in the world. And this kind of follows on quite well from the solid structures lecture that we had, which was lecture 2. I've also got a video on MOFs. This follows on nicely from what we did with the D block and the coordination complexes. And then finally, there's a video on energetic materials, which follows on a little bit from the P block lectures. It's mainly focused on nitrogen, and a lot of these are nitrogen containing compounds. But yeah, first up, as I said, we're going to be looking at the electrical properties of some solid structures. So to help us work out whether something's going to be an insulator, conductor or a semiconductor, we're going to be using something called band theory. And this is kind of a bigger built up version of molecular orbital theory for larger structures. So when we're looking at the electronic structure of discrete molecules like CO2, N2, molecular orbital theory works fine. We've got a handful of atomic orbitals that come together to make a handful of molecular orbitals. It's quite easy to use. But when we're looking at things like these extended solid structures like metals in metallic bonding structures, or covalent network structures, stuff like silica that we saw, SiO2, that sort of covalent network, those things are bonded infinitely, essentially. They've got so many atoms in them, and we're talking on the scale of 10 to the 23, sort of like a trillion atoms in there. There are going to be so many molecular orbitals. We don't really think of them as molecular orbital theory anymore when we think of bands. I have also got a help sheet already online on band theory, so if you want to read it, it's quite similar to what I've got in the first few slides of this lecture, but it may be helpful. So where does band theory come from with respect to molecular orbital theory? So if we start with atomic orbitals, we'll start N here is the number of atoms we've got. So when we've got an atom on its own, it has an atomic orbital, say. When we've got two atoms coming together, each of them has an atomic orbital, and they get split into a higher energy antibonding orbital and a lower energy bonding orbital. Then we can put in a third one, and we get three atoms, and they form a bonding and non-bonding and anti-bonding. And this goes on, and as we put more atoms in, we get more molecular orbitals out. And then, say we get as far as having 20 atoms in a structure, we get the lower in energy bonding orbitals, and there are now 10 of them, and the higher in energy anti-bonding orbitals, and there are 10 of them as well. But if you see, the gap between each of these molecular orbitals gets smaller. And this is only for 20 atoms. As I said, we've sort of got a trillion atoms in, say 50 grams of iron, which isn't a great amount of iron. There are like a trillion atoms in there, trillion molecular orbitals. They're going to make, the gaps between the molecular orbitals are going to be so small, they almost, they do form what's called a continuum. And then we don't think of molecular orbitals anymore, we call them bands. So that's what this red box is. It's just there are so many molecular orbitals, all at such a similar energy, not the same energy, it has to be stressed, because then the Pauli exclusion principle wouldn't be satisfied. Remember, you can never have two electrons in a compound with exactly the same quantum numbers. So these are all very slightly different. But close enough in energy that they've essentially just become one continuum, which is called a band. Now we've got our bands, and let's see what happens when we put electrons in these bands. And we'll do it again starting from like an atom and working up to the band. So if we take lithium as an example to start with, it's got a 2s1 electronic configuration. So here is our s1 electron of lithium. Now if we had two lithiums, so like just an Li2, we'd put both of the electrons in the bonding orbital, and there'd be no electrons in the non-bonding orbital. Now HOMO refers to the highest occupied molecular orbital, which is this one, and LUMO is the lowest unoccupied molecular orbital. And that's, yeah, therefore, it's a self-explanatory name. If you continue working across, we get 3 lithiums. We then have the pair in the bonding orbital, pair in the bonding orbital, a single one in the non-bonding orbital, and nothing in the anti-bonding orbital. And then we get up to 20, and we got 20 electrons, all as pairs in the 10 bonding orbitals, nothing in the anti-bonding orbitals. And if we get to this essentially infinite number of electrons, the same thing happens. We've got a half-filled band. Now, a half-filled band is essential to conducting electricity. Like, this is what allows electrical conduction. So yeah, I've got it written here as well. Partially filled bands allow conduction, and this is because the electrons can move freely. So there's, as I was saying, all of the fake molecular orbitals are close enough in energy that the electrons can just hop around, and therefore, they can conduct electricity because there's space for them to move. There's empty electron areas that electrons can go. So because lithium starts with a half-filled s orbital, it has this half-filled valence band. So it's called the valence band because it's essentially the band where the valence electrons are. So these bands happen for all of the orbitals, and we'll see it's important on the next slide for the outer, sort of the further away than the valence bands. But so the 1s orbital will have a band as well, the 1s band, but that one's going to be completely filled. It's the valence band that we really care about because that's where this 1 electron is, and it's a half-filled valence orbital, so it ends up with a half-filled valence band. What happens then if we take magnesium? We saw lithium has a half-filled s orbital, and that gave us a half-filled valence band, and it's this partially filled band that allows us to conduct electricity. But if we do the same thing with magnesium, that has a filled s orbital, it's got 2 s electrons, and we see on its own it's got 2 s electrons. Put it in 2 molecular orbitals and they're both filled, 20 and they're all filled, and that leaves us with a full valence band. And therefore, there's no partially filled band. How can it conduct electricity? And we know it does. It's a metal, and magnesium conducts electricity. Well, that's when we need to consider the bands of the other orbitals that it has. So the valence electrons of magnesium may well be in the s orbital, but there's still going to be a p orbital also. And this p orbital, even though it's unfilled, makes a band also, and this band is called the conduction band. And this is why I had the HOMO and LUMO on the other slide as well, is that the highest occupied molecular orbital sort of corresponds to this valence band, and then the lowest unoccupied molecular orbital becomes the conduction band. So the conduction band is the lowest unoccupied band essentially. But with this P, so I've got the 3s and the 3p bands here. The 3s one, we were saying, should be completely filled, but the 3p band actually is quite low in energy. Like the 3p orbitals are quite similar in energy to 3s. When you make these bands, they actually overlap, and the bottom of the 3p band is lower in energy than the top of the 3s band. So some of the electrons will leave the 3s band or the valence band and go into the conduction band, and then we do end up with a partially filled conduction band, and then we can get electricity flowing. We get conduction, and that's why things like magnesium, even though they seem at first like they should be a tricky case, they do still follow the rules, and we do still get electrical conduction. So that's why metals can conduct electricity. Like, to be able to conduct electricity, we have to have that partially filled band. So what about the other two options? We've got insulators and semiconductors. Well, they still have this band theory, sort of the covalent networks. They've still got an infinite number of atoms for all we care, so they form bands. But in the case of semiconductors and insulators, the valence bands are both full. So I've got shown down here. Now the next band up, so the lowest energy unoccupied band, the conduction band that we were talking about, this time is higher in energy than the valence band, and is the gap between them, which is called the band gap, which determines whether something's going to be an insulator or a semiconductor. So on the left here, I've got the band diagram for an insulator. So we've got the valence band down the bottom here, completely filled, that's why it's in black, and the conduction band up here in red is completely empty. Now the band gap, this Eg, is very large between them, So you can't really get anything making this jump up into the conduction band, and that's why it's an insulator and won't conduct electricity. On the right though, you can see that we've got a similar diagram for a semiconductor. It's got the same completely filled valence band, but its conduction band is much lower in energy, and this band gap is actually quite small. So what that means is where this band gap is quite small, thermal energy can promote electrons into the conduction band. And when that happens, we end up getting a partially filled conduction band. And that's what I've got drawn here, like the valence band that was filled on the last slide has actually had some electrons hop up into the conduction band. Because this energy gap is quite small, thermal energy can do it. As we'll see in the next few slides, light can do it as well. And then we get a partially filled conduction band, and then electricity can flow. It conducts. And because of this, one of the properties of a semiconductor, which I've got in big because it's important, is that conductivity increases with temperature. And that's because as the temperature increases, there's more thermal energy, more electrons can make this jump from the valence band into the conduction band. And if there are more and more electrons in here, then there's more electricity can be conducted. So that's how semiconductors can go from insulating to conducting electricity, and how it's shown with the band theory. Let's put this into a bit of context then, since that's the point of these videos, and we'll focus on 3 examples of how semiconductors can help us deal with some societal problems, and how they've actually been used throughout history. So the first one I'm going to look at is photovoltaics. This is essentially how we can generate electricity from the sun. This is the science behind solar cells, solar panels, and all of that. So I've got solar panels down here in the left, the ones that you see on on the roofs of houses, in fields if they're in a sunny country harvesting sunlight. Then also there's my favourite example of solar cells in use, the International Space Station. In space, they need a lot of electricity to do all their experiments to keep them living. I mean, they actually purify their pee to drink as water, and you need power to do that. To get the electricity, they use these big solar panels on the side of the space station, because there's no other way to get electricity in space. So how do these solar cells work? Well, they consist of 2 layers of semiconductors, one grown on top of the next. And these semiconductors can actually be what's called doped with additional atoms, and this changes the property of them. So the typical semiconductors we're using for solar cells use silicon, but if you can add small amounts of additional atoms that can either add electrons, so this is called n-type doping, so then the semiconductor has more electrons than it normally would, or you can add holes. Now, holes are essentially what's left, the positive charges left behind when an electron is taken away. So essentially, if you add an electron-rich atom to the silicon, you'll add electrons and get an p-type 1. If you added an electron-deficient dopant, then that dopant would take away an electron and leave a hole behind in the semiconductor. And these 2 layers of n-type and p-type semiconductor will be grown onto each other, so they've got a really perfect interface. And this interface is neutral because the extra electrons and holes will balance out. But what happens is that when sunlight hits and more electrons are created, more electrons and holes are created, they're only able to move in one way. So that's where the circuit comes into it. So I'll draw it quickly like that. So you've got this semiconductor, and we've got the n-type on top and the p-type on the bottom. Now the little region around the line in between them will be neutral until sunlight hits it, and then more holes and more electrons will be created, but they'll be separated, and the electrons will go to the top, which will be negatively charged, and the holes will be at the bottom, which is positively charged, but they can only move in one way, which is this direction, towards the negative charge. So they can't go both ways to recombine. So what happens then is we can put essentially a wire go into a light bulb, say, or any other electrical device. This is a light bulb. Going back round to the positive side, and then when light hits, the electrons go round in this way and create a circuit, create a flow of electrons. We get an electrical circuit. And yeah, obviously, if you're trying to do it as a solar power plant, you wouldn't put a light here. You'd have some way of storing the electricity. This is essentially how solar cells work. And as I said, they're mainly made of silicon. It is quite tricky to get the head around. These are a bit more advanced. I'm not going to ask you to know how a solar cell works in the exam. I just want you to see how semiconductors can be used. And if you would like a probably better explanation, there's a YouTube link here that I'll put in the description to a TED Ed Talk, so it's an educational TED Talk of someone explaining solar cells. The other way I wanted to discuss how semiconductors can help us in the fight against climate change and addressing some societal problems is through how it can be used to make hydrogen as a green fuel. So we've talked a bit in the lectures before about hydrogen being a really promising green energy source. It's got really high energy density with respect to its mass, although not for its volume. But it's really cleanly burning. Like if you combust hydrogen, water is the only byproduct, and I've got absolutely no problem with water coming out of an exhaust pipe. The real challenge though is to get hydrogen from a non-fossil fuel source. So in the hydrogen lecture we looked at steam reforming and how we take methane or natural gas and get hydrogen from there. But then obviously it's not really green hydrogen, because although it burns cleanly out the back of the car, you've created loads of CO2 to get the hydrogen. We can get hydrogen in a green manner though, and that's by splitting water. So we talked about this a bit as well at the end of the hydrogen lecture, splitting water into H2 and O2. Therefore, water is a very clean source, and this is usually done electrochemically. But then the problem was, where do we get the electricity from to split the water? Because that's going to be coming from some sort of power plant that produces loads of CO2 probably. Now, is there a properly clean way we can get hydrogen fuel? And the answer is kind of yes. Another quote I've got down here, I actually put in my PhD thesis as well, because that was on hydrogen fuel. I find it a really nice one. It's from Jules Verne and his book The Mysterious Island, because this came out in the 1870s sometime, like 150 years ago now. And it was a sci-fi book, and back then he's saying that water will one day be employed as a fuel. Hydrogen and oxygen can be used either on their own or together, and will have an inexhaustible source of heat and light. And he's kind of right. But back then it was just science fiction. But now we've actually found ways to do it, and it could become science fact. Let's look at how we can split water using the sun then, and how we can develop what's called a photocatalyst. So a light activated catalyst that can make hydrogen from the water. So I've taken this figure from this review down here. And a couple of times in the videos for this lecture, I have taken the pictures from actual research papers. So if you're interested in seeing any of this research further, you can always look them up. And I think you should have access through the university. So in the first panel, it shows a bit how the electrolysis of water works with a photocatalyst, but in an actual electrochemical cell. So an electrochemical cell has a positive and a negative side. So the positive side's over here, and that's called the cathode. And then the negative side is the opposite one, and that's called the anode. So then when light hits the titania, which is another another semiconductor, exactly the same thing happens with all the semiconductors. So light is enough to make an electron jump from the valence band, the VB, into the conduction band. They've already put an arrow on, but I'll put another one. And when this happens, a hole is left behind, and that's where this positive charge comes from. And that oxidizes water into oxygen. The electron then goes through an electrical circuit to the negatively charged anode, and it's the electrons that give it this negative charge. And at the anode, H+ is reduced into actual molecular hydrogen, which is what we really want. Now this is nice having these two electrodes and this circuit, there's wires through it and everything. But how can we actually do it in a better way? And that's where people are investigating what these solid photocatalysts, and they're eliminating the need for all of the putting a bias through a wire and everything by putting the anode materials, this platinum, directly on a particle of titania, which is TiO2. And in that way, exactly the same chemistry happens on this one particle. So we've got the diagram here showing what happens to the electron when light hits the titania. So again, we've got the valence band and the conduction band, and when light hits the titania, then an electron is promoted up into the conduction band, leaving a positive charge on the titania, and this is where water can get oxidized to oxygen again, much like at the working electrode. The platinum then can take the electron directly from the titania that it's actually chemically adhered to, and that can then do the reduction of H+ into H2. So this is the sort of thing we're actually investigating a little bit in the group I'm working in at the moment. No, I'm not, but some colleagues are. And it's the development of materials like this, photocatalysts that can more efficiently utilize light as a semiconductor to split water and make other reactions happen. Now, when they're developing new photocatalysts, one of the most important things is the wavelength of light that this occurs at, like the actual semiconductor, the electron being promoted to the conduction band. Because sometimes it only happens in UV light, which is perfectly fine if it's outside and it's hitting sunlight, for example. But when you're inside, there's not actually much UV, otherwise, you'd get sunburn in your living room. There's only visible light. So we need to change the wavelength of light that excites the electron into the conduction band. So that's where semiconductor research is focused at the moment, or a couple of areas that it's focused at the moment, and how it can help with the climate change problem.